Okay, it's my very great pleasure to introduce you to amazing Kyung-Hoon Cho today. He's a professor of computer science and data science at New York University and a senior director of frontier research at Genentech. He's also a CFAR Fellow of Learning in Machines and Brains and an associate member of the National Academy of Engineering of Korea. He is also a founding co-editor-in-chief of transaction and machine learning research, and he was a research scientist at FAIR, and he received the Samsung Hwang Prize in Engineering in 2021. Without further ado, please take it away.
Well, thanks. Thanks for the very generous introduction. So, well, it's great to be here, actually. AI too. I've only heard of this, the elusive placement over and over, but it actually exists. But just hidden among all those fisheries, and then you had the fisher, you had the scientific companies and so on. This is cool. I could have actually talked about the what we're doing at the Persian design, part of the Genentech, and tell you about how machine learning, different paradigms of machine learning can all come together in order to help us find the better antibodies. And now we're going to more small molecules as well by working together with the antibody engineers and then synthesize and testing them on all those things. But Seattle is way too close to San Francisco, and the Genentech comms people might show up and tackle me as soon as I start talking about this. So I decided to go talk about something that I don't really work on at Genentech, but at NYU. And I'm going to start by talking about what Leon said in 2015. I believe it was one of the talks at the ICML back then. And this is almost always what happens in machine learning, is that the Leon says something, and about anywhere between 7 to 25 years later, the whole community realizes that, actually, Leon told us this already 10 years ago. So I thought, okay, this is probably a good time for us to go back about 9 years and then see what Leon said. And then one thing that Leon pointed out back then was that the machine learning has been extremely lucky that we could actually rely on a single experimental paradigm that is essentially to hold out some of the data points and then see how well your algorithms work or your models work on the held out set. And then you declare the success only if your algorithm actually works on that held out set. And that's been going on over and over. Now, when did it actually start? It's a bit debatable, but I think you can find some of the papers from the 70s already talking about this paradigm of the training, validation, and testing. But the consensus is about, mainly about, let's say early 90s, people started to. But what Leon also astutely made an observation back then, he said, okay, this experimental paradigm is reaching its limit. So today I'm going to agree with Leon, finally, 9 years later, and then tell you that, okay, I actually agree with him. And then there are a few different aspects that we probably need to think, put out more efforts in. Beyond, of course, buying all those GPUs from NVIDIA and AMD. I heard, you guys are using the AMD GPUs. Great, yeah. We've been using that at NYU for a few years now, and then it's pretty painful, isn't it? But let's talk about what we mean by the tested accuracy as the one and only criterion that has been driving machine learning. When you think about just a very simple machine learning paradigm, there are 4 stages. One is data collection, and often, as researchers, we don't even do the data collection. We're going to just pray that someone else is going to do the amazing data collection for us. We're going to take the data, and then we are going to go into the stage of the training or learning. That is, we are going to try to minimize the loss function that is defined with respect to the model as well as the data set that we're going to use, training set. And then in the inference stage, we need to also solve another optimization problem, often can be cast as a minimization of the energy function. Fine. And then finally, after everything is done, we're going to evaluate this model on the test set. And if the test set accuracy is higher than whoever else has reported, we declare success, write a paper, submit it next month, and then we move on to the next project. So that's been going well. And then one thing is that, okay, so we've been really focused on the evaluations, like how to compute the loss on the test set side, to the point that we started to kind of hide all those details from the earlier stages a bit too much. Because, in fact, all those stages involve a lot of, let's say, complicated things. So, if you think about the stage between the data collection and learning, there's a huge amount of the work on assumptions that we need to make, because nothing works without assumptions. Now, we often feel like, okay, nowadays, you look at Twitter and then, or the X, I guess, X, it feels like all you need is a lot of GPUs, transformers, and then maybe Hugging Face transformers or the OMO code, I guess now. Yeah, that code, and then you had the, I don't know, Lightning Studio, click, click, everything works. But of course, that actually has a lot of implicit assumptions behind the practice we have built. Oops. And then, of course, between the learning and inference, there's a huge step of the optimization and model selection, hyperparameter tuning that goes in. And then that one often is now considered as a, well, we just use the atom W, and then we're going to increase the learning rate somehow, and then use a cosine annealing over and over, and then you have to hope that everything is going to work out well within about 2 months. After which, our model has seen, I don't know, 3/4 of the trillion tokens, right? Yeah, something like that. And then, of course, inference also is actually problematic part. We say that, well, we use a GPT-4 or the whatever, and the almost 7B, and then we generate something. But then what is generation? It's a distribution that is defined over the combinatorial space. And in fact, the probability on the set of the probability assigned to a set of the infinitely long sequences may not even be 0. So then what are we actually doing? We're not actually sampling from the language model distribution. Everyone reports the perplexity, but then we never actually sample from that. You're going to use, I don't know, top case sampling, or there are a few, like all the speculative decoy, blah, 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 right? So actually none of us actually sample from the distribution or know what the distribution from which we're sampling. Anyway, but we don't talk about it. We simply say that we call the API, right? And then it's relatively straightforward these days. And in particular, if you use a GitHub Copilot, you actually don't even have to write anything. You just write comments, and then you have to pound, generate text of the length at most 250, and then make it not repeat as much. Enter, you wait about a second and a half, there's going to be a function, right? And then you tag, that's it, that's great. So today I'm going to talk about, this talk has 3 parts. Probably I won't be able to cover the whole thing. Probably I'll try to cover the first 2, but if I talk fast, I guess I can cover the last part a bit as well. But I'm going to go the opposite direction. So I'm going to talk about what do we mean by these language models generating something really interesting. Then I'm going to talk about is there something that we can learn from by looking at the optimization a bit more carefully. And then finally, if I have time, I'll talk about the importance of the assumption and then why assumption now matters even more so than before. The first part is on the consistency or the inconsistencies in large language models. This is a work that was led by the Angie Chen, who I believe is going to graduate soon. So if you are looking for some amazing scientist, Angie is the one that you want to talk to. And this paper is online, it's on TMRL as well as on arXiv as well. So when we think about the inference or generation of language models, what you realize is that in fact, we never actually we can never ask a question that is fully specified to the point that there's only one answer. Almost always, the questions that we ask these language models or any kind of machine learning systems do tend to have the ambiguity to the point that there can be many different answers. And if you think about it, that's only natural just because of how natural language is. It's filled up with ambiguity as well as redundancy. And then that's the reason why the learning works. Without ambiguity, learning a language doesn't work at all, actually. It's impossible. So that's great. But then the issue is that, okay, then how does this model actually choose the answer? And as I just told you, we are actually not sampling from the language model distribution at the end of the day. So what are we actually getting? So in order to resolve that kind of issue, what people are doing is that, well, we're going to ask the language model to just choose one of the answers that is pretty likely, and then give us the answer. And then that is actually often what we refer to as or what people refer to as, I really don't like this term, but chain of thought processing. Or nowadays, I think that there's like the tree of thoughts, forest of thoughts, skeleton of thoughts. Maybe at some point there's going to be a universe of thoughts. But anyway, so the idea here, everyone knows very well, is that you go to the language model, can be the conversational version or whatnot. It doesn't really matter. You ask it to think a bit more carefully, and then tell us what was the step by which the answer was arrived at. And then that thought of chain or this kind of introspection can be thought of as, okay, doing argmax on the latent variable that decides which answer is going to be most likely. And then, of course, the question is that, okay, if it is going to be called a chain of thought, then, does it actually reflect the process of the thinking that as we anticipate, as we think the thought process should happen? And indeed, if you just try it out, okay, this is the example from November last year, so I'm pretty sure these all have been patched already. But anyway, so trust me, it was very easy to make it. And then I was a bit cheap back then, so I didn't pay OpenAI for access for the GPT-4. It's a GPT 3.5. But you can actually try it out very easily. And then sometimes it looks like that is the case. The answer can be correct for the correct reason, but sometimes the answer can be incorrect, but for the reason that makes sense. So I can see why the model made arrived at the incorrect answer following the steps. But of course, you try it a couple more times, and then you notice that that's not always the case. It's often that the answer is going to be correct, but for the incorrect reason. The answer is going to be incorrect for the incorrect reason that is not consistent with the incorrect answer. Sometimes answer is going to be incorrect, although the steps were all correct so far, but then the model kind of decided not to use that steps. So then, of course, what is going on here? Because at the end of the day, the goal of language modeling, or the goal of using language modeling for our benefit, can only be achieved if the prediction, if the way in which the answers are produced by these language models is predictable under our kind of way of thinking. If the model makes some mistakes that are just unpredictable from our kind of thought process, we can't really use it for anything other than a relatively straightforward, let's say, things that speeds up our productivity, but nothing that makes us do way more than what we imagined we could do. Obviously, a lot of people, including people here as well, have been looking into it. This is one paper from, I think, the Anthropic, Lanham et al. 2023 last year, talk about, okay, so what if we modify some of these chains of thoughts and then see what happens? And then we can probably ask all those questions. And then the answer was that, sometimes it looks like a good thinking, good, let's say, reasoning there, but sometimes not. And similarly from NYU, Sabra et al. Last year, kind of, let's say, narrowed it down a bit and then said, okay, so for the deductive reasoning task, now we are going to introduce a synthetic setup where we ask the language model to give us a statement together with the proof. And then because proof is going to be in a particular way, we'll be able to systematically check the correctness of the proof. Thereby, we can check whether this reasoning process makes sense or not. This is also work done by the Safarov, the Kim, and the Hong. And then it makes sense. Sometimes it does well, sometimes it doesn't well. But when it doesn't do well, we know exactly when is when the number of the proof steps is greater than the few of the examples that were given, or if the statements is longer, or some of the things are much rarer, let's say, situations. And then what that means is that this model seems to do really, really well on the kind of examples that we actually provided examples for, but probably not solving the problem in a way that we wanted to solve. Because we know that in this kind of, let's say, deductive reasoning, if the proof is being done in a way that we anticipate that deductive reasoning should be done, then it really shouldn't matter whether the statement is longer, shorter, proof should be longer or shorter. So the fact that these models are actually sensitive to these, let's say, small superior stuffs already tells us that, absolutely, there is some difference between us and these language models. Unsurprising, but if you go through the X these days, it's actually a surprising thing. No, language models are not like us. It cannot be the case. So what it tells us that, okay, these language models clearly don't reason like we do, but then how do we actually figure out how they are not reason like we do? And then of course, we can continue to produce even more data sets, and then just run it until the point that, okay, we have enumerated all the data sets that we care about, and then on those data sets, these language models and we are actually working in the same way. That's fine. But another way to go about, because at the end of the day, data set space is kind of infinite, this combinatorial space is gigantic. So try to look at what are some of the minimal kind of consistencies that we would anticipate from these language models, so that if these language models are not good, or they do not exhibit this kind of minimal type sets of the consistencies, we can probably just say that, okay, we need to do something more before we kind of, let's say, use it for something more sophisticated. So before I move on, let's put two kind of definitions that are extremely naive and also ambiguous. But it's necessary just because of the natural language. Language really doesn't allow us to be too precise. So two of those definitions, one is a semantic equivalence. So of course, if the two texts have the same meaning, we're going to say that they are semantically equivalent. How are we going to tell that? We're going to read them ourselves. If I read, let's say, two texts and then feel like they have the same meaning, we're going to say they are semantically equivalent. Now, the second one is a replacement. The idea is that here's a template, and then I'm going to have a marker, and I'm going to plug in another, let's say, text there. Now, this seems like a very, relatively straightforward thing. Not at all in language, because we will probably have to both modify template as well as something that we want to plug in. In English, actually, it's relatively straightforward. But if you're thinking about another language, it's very challenging. So how are we going to do it? We're going to do it ourselves. We're going to do it ourselves. Obviously, not the first time that people have thought about it, and in particular in the context of this kind of larger scale modern language models, Elijah in 2021 thought that hold on, are these masked language models like the BERT really, really good? And then what they said that okay, we need to check this kind of, let's say, self-consistency. If the questions were semantically equivalent, the answer should also be semantically equivalent. Pretty straightforward, but then they found out that a lot of the language models back then did not exhibit that kind of property. And then I just tried it again in November when I was preparing this talk. And what was it, GPT 3.5 Turbo Instruct 0915 did not exhibit this kind of, let's say, very simple self-consistency there. Another example is from last year from the Berlin et al. I think it's from the Anthropic using the OpenAI GPT. They called it like the, I don't know, the reversal curse. I'm like, I don't know. That's a weird name to use. But let's call it equivalence consistency for now. So if the word is, right, is used to indicate that the subject and object are equivalent, because that's not always the case. Is can actually mean anything. Like could be superset, subset, there's too much ambiguity there. But if is used for the equivalence, then this language model should know that we can replace one of them or plug it into a template, and then equivalence is maintained. Turned out that that's not necessarily true, well, back then with the GPT form. And then you can imagine what are some other, let's say, minimal consistency you can imagine. These are really simple things, right? Nothing complicated. And then we thought that okay, maybe we can think about the two different things that are really interesting. One is hypothetical consistency. So what is hypothetical consistency? We want to ask the language model or any kind of model what the answer to the question would be had it been asked that question. And then we're going to ask the language model the question as it is, and then we want the answers to be same. So something like, what did you have for breakfast this morning? Let's say I asked you that question, you answer me. And then later on the same day, I'm going to ask you that, what would be your question to the answer to the question, what did you have for the breakfast in the morning? Your answer probably should be exactly the same as before. Right, very straightforward thing. But this one is interesting because in a sense that this has a two kind of there are two ways to solve this problem. One is to know that this kind of templates are all kind of identity function, or the other is that I should be able to simulate myself and then see what my answer would be, and then you have to figure out this answer. And then sounds really relatively straightforward. And then one thing I want to emphasize is that the correctness, we don't really care. These models can be incorrect as much as it wants, but we want it to be consistently incorrect or consistently correct. So again, this one I tested with the Text DaVinci 03 from, let's say, November last year. Sometimes it's consistent, sometimes it's not consistent. And these examples are extremely easy to come up with. You just type it and then asking okay, what will be the answer to this question? It gives me the different answer. So how do we actually check this? Turned out it's not trivial at all. Because the semantic equivalence is in the eyes of us, so we have to check it ourselves. So Angie came up with the idea that we're going to prepare a set of, let's say, identity prompts, and then we're going to prepare a set of, let's say, questions. Often just complete the, I don't know, like the following, let's say, 4 to 5 words or something like that, and then we're going to ask a bunch of models the answer first for those questions. And then we collect all those answers, make into a multiple choice question, and then ask the language model again that, okay, so what was your answer to this question among these, the multiple choices? And then, if the model knows how to simulate itself and then knows that, okay, I already answered in this way to this question, so thereby this is the answer. Should be able to do that. People can do it, by the way. Yeah, you can all do it, try it very easily. And then we just check what the accuracy is on picking out this own question. And then we make sure that all the answers are unique. And then we also include the correct answer as well from the Wikipedia or whatever the data set we use to create this one. So that's like the human version, right? People can almost always pick them up. But anyway, so it turned out that most of the models kind of fail pretty miserably, as in they can't really figure out which was the answer. And then the bigger models tend to do better. GPT 3.5, GPT 4 does slightly better, but it's like the 25% accuracy when the chance accuracy was 20%, not that great. Okay, so it really has a difficult time figuring out what kind of answer it would have given already. And then what it actually says is that, these language models, in one way to think about it, is that they do not model their own reasoning process and cannot really simulate themselves. And then this has, the interesting kind of, let's say, consequences. So that was a hypothetical consistency. So the second one is an even simpler one, straightforward, compositional consistency. The idea is that, okay, so something like, well, I have this arithmetics. Now I'm going to replace some parts by asking the language model what the answer should be, plug it in, and the answer should be very consistent, right? And then we can test it relatively straightforwardly by creating this kind of examples very easily, all randomly. And then this is one example I just tried. And the first time I tried, I ran into this. Again, text DaVinci 03, 4 factorial is, it knows it perfectly, 24. Kind of say, this is nice because this is a kind of thing that I would just memorize, but it was able to give me the postal explanation why it is 24, and 24 is correct one. 4 plus 4 factorial is 28. That's also correct. So I asked it, okay, so you know that the 4 factorial is 24, so I'm going to replace the 4 factorial with the 24. So 4 plus 24 is 48. And it's okay to be incorrect. I mean, you ask people on the street, the 4 plus 24 is, some people will make mistakes because they're like, oh, okay, so maybe 29, okay, something like that. But then the issue is that these two are not different. If it's at 48 here, I'll be very happy, and I'm like, okay, this is actually a great. But it's not really the case. So what we did was to produce a very simple set of nested arithmetic expressions, max steps 5 only, operators only 4 operators, plus minus division and multiplication, and up to 3 digits only. And then once we create them, what we're going to do is that we're going to look at all those, the parentheses, the expressions within the parentheses, ask the language model to get the answer from. And then what we're going to do is we're going to plug them in and then create all those what we call the compositionally consistent, let's say, prompts, or the consistency check prompts. Yeah. And then we see if the answers to these two questions and the original question are same. They should be same. They should be same. If our calculator actually gives a different answers to these things, that's not that great. We built a very lousy calculator there, an expensive one at that as well. And then it turned out that these models are not doing too well either. So the GPT-4 is included in this figure. Yeah, they're still getting less than 50% of the examples that we gave with the consistent answers. And then often the issue is that it's not about the correctness here. It's a lot about the consistency. Again, correctness, we don't really care that much. These models are going to make mistakes because there's a stochasticity involved in this one anyway. Now, what this actually tells us, there are actually 2 ways to think about it. One is that, okay, so this model really doesn't know about the hierarchical nature of the math expressions, but then this actually check has one major issue, and then this makes it really difficult. It's a lesson we learned, at least I learned about how difficult it is to come up with this kind of check, because there's one way to get the perfect consistency in this case, that is to just build a gigantic table storing every arithmetic equations and then get the correct answer every time. 100% accuracy guarantees 100% consistency. Although what we see is that the rate at which the correctness is growing is slightly faster than the rate at which the compositional consistency grows. So what that means is that even when these models are getting more and more correct, maybe these models are not becoming more correct for the right reason, where the right is defined as what we want it to do. So but then so far, it doesn't look like these models are actually solving these arithmetics, for the right reason. Unsurprisingly, at the end of the day, it's a fit for a neural network with your regressive connection. So there are some mathematical operations that probably require more compute than let's say a transformer with the ON operation with the fixed depth actually can solve. But there are too many magical thinking, so we thought, okay, let's see if that magical thinking is actually correct, because that would be nice. Turned out that's not the case. And then what it actually tells us is that these language models solve amazing problems at an amazing rate, but not necessarily for the right reason. And then we're not the only ones who've been actually looking into this. Some of the work from the MIT, UW, all those places actually tell us that it turned out that these models are too reliant on the surface level representation of examples, that actually is a kind of, let's say, a piece of the evidence telling us that this essentially, I think, of maximum likeliness matter, there is a table with accounts. So what, for instance, this is one of the hilarious example. Is that the GPT, it is just GPT-4 arithmetics, just a 2-digit, if I recall correctly, addition, and then base 10, it gets 100%. You ask it to solve the problem in base 9 and then provide the questions in base 9 numbers, the accuracy drops dramatically. And then you have to really, because how things are represented at the surface level matters a lot if you do the table lookup. You can't really solve the baseline that easy. I mean, and then you have a lot of people actually ask me whenever I bring up and I say that, oh, this is an amazing example and I love it. And they're like, but you can't do the baseline arithmetics. I was like, yes, I can't. I mean, but that's not the point here, right? The point is, to make extraordinary claims about what these language models can do and then what kind of reasoning process it takes, you have to provide extraordinary evidence or a very simple, dumb, let's say, counter example. And then this is an amazing counter example. But anyway, so how do we improve consistency? I don't know. But essentially what I'm thinking increasingly more so is that the maximum likelihood estimation on a passively collected data is just limited. I mean, in fact, we already knew that ever since like the 1980s or something. So that's actually one of the reasons why I'm spending time a lot on the Genentech, because that's actually where the interesting thing happens, where the data is collected ourselves, and then how do we collect the data is driven by the machine learning and everything. And then also I'm looking a bit into the causal inference just because I'm teaching a course this semester. Big mistake, but like these two are the two directions that I've been thinking a lot these days. Now, one huge caveat, OpenAI doesn't reveal much about the training models and deployment. And in particular, I'm very concerned about the deployment side. They said that they give the model name and then like date and every version, but then when they deploy it, what they're going to do is not to actually sample from the language model again and again. They're going to put a lot of, let's say, various tricks to make the decoding better. And then they're going to put all those different filters. And then we actually don't know what those are. So in a sense, we may be actually not listening to the collective intelligence of all the humanities that have been collected on the web, but we may be just listening to what Sam Altman wants us to listen to. And then I'm not a big fan there. So most of the conclusions we draw from these models, especially via the API access, are likely to be highly misleading at some point in the time in the future, or likely misled by OpenAI themselves. So including my own work, I would say that I actually recommend most of the people not to actually trust any of the papers' conclusions if they only run the experiments with the OpenAI's GPTs. So do not trust too much of what I just told you. Well, of course, now with the OMO, hopefully it's going to get better because OMO actually released a training code as well. But we're still looking at, our team was looking at the training code. I think it's not full. It's not completely full in the sense that there is no, let's say, how the online evaluation happens. So if I wanted to run just the code as it is, I don't think we can actually reproduce exactly how the online. So was there some kind of orchestration?
It's all there. You should be able to reproduce your
No. Reproduction is fine. The model is fine. But let's say if I wanted to get that on a bunch of the instances in AWS, and then I'm going to start training it. You guys wrote something about what was it that you continuously do the downstream benchmark on the fly as a training.
Yes.
So that one, did you actually?
Half of them are in loop. The other one is through like a separate framework.
Right, and then what do? Do you just run it on the parallel? So whenever there's a checkpoint, I see. So nothing
There's nothing
dramatically.
fancy, yes.
Okay. I can tell my students about it. Okay, that's good. That's very good. But yes, so
email there works. You can just.
This one works. I can. Okay. Well, all right. Okay. Expect some emails. Yes. All right. But yes, so I think it's going to get better. So that was the part one. I'm going to go into the part two. Is there any, I don't know, comments or thoughts? Yes.
So just thinking about like the way these models are trained, and we've got some previous examples. So like one of the works you showed was about it was my work actually about like knowledge, and you showed some example with math. I think they're different in a sense, but overall, I'm curious about your thoughts about consistency. Like, should we even expect language models that are training this way to be consistent?
Yeah. So I mean,
Like even if let's say they get zero loss from the data, right? They fit the data perfectly. Do you think that even in this case they should be consistent?
It doesn't necessarily have to be consistent, just because there are so many different ways to solve the problem. And then the one way in which we want our language models to be is one of infinitely many other ways in which the problem can be solved. So just looking at a passively collected data that represents only a tiny fraction of the large combinatorial space, of course, we can't really expect any models without any strong assumption to generalize systematically outside that easily. So yeah, I mean, I don't think that's actually particularly possible now. Big hope is that because we have, I don't know, like a million people writing, ICML papers every month, or I don't know, something like that. Maybe the exploration is going to allow us to stumble upon one of the solutions. But then again, that only works for the problems that we know how it should be solved. So for instance, I'm working on the antibody design. We have zero idea how we can actually design antibodies, the better antibodies ourselves. Showing the, let's say, newly, produce the antibody candidate coming out of these generative models and whatnot. You show it to the best antibody engineers who have the 30 years of the experience at Genentech. They can't tell you anything other than oh, this is completely wrong. It's not going to do anything. But is it going to be good? Maybe, maybe not. Yeah. Yes.
Yeah. I have a question about language models do not reason like humans, right?
Yeah.
And a lot of people criticize the fact that we try to teach those chain of thoughts, some algorithms that we humans think they're the right algorithm to learn a certain task. But people say you're being unfair to the model because the model might be using a different algorithm internally to perform certain tasks. This is why it's not consistent, because you're trying to teach it something different from what it knows. So how do we know the internal reasoning of the model? Is that the case really, or we're being really unfair to the model?
I mean, to be strict, I don't think we have to be fair to these models. It's a piece of software, so we don't have to worry about it not that much. But let's say we have to be fair. But that's why I think it's actually much more important for us to think about this kind of very minimal set of the simple consistencies that we need these language models to be aware of or they possess. Not that we're not throwing all those complicated things actually at this point. These are like not even the complicated thing, like the hypothetical consistency. It's just identity function. There's a tautology, and then identity doesn't require actually many different algorithms. There's one algorithm. There's the pass whatever has come in. And then these models can't even do that one. So that's why I think it's really about the minimal consistency. And then this one was a really great example. Because this is really just telling us that, okay, so if there are two questions that are equivalent, just map it to the same point in this vector space, and then decode out anything that would actually be decoded out from this one point that should be symmetrically equivalent. Turned out that that's not the case. Oh, did you show it already? 2021? But yes, okay, so that was a part one. And then this actually, these questions are great because we're going into the part two about the optimization of it. And this is the work led by Michael who is a PhD student. He's not graduating anytime soon. So, when he does, I'll let you know. But so one thing that you notice, especially increasingly more so, is that the people are going to talk about, well, it's almost always like that 90% of the machine learning papers are all about the, how to come up with the regularizers. So they're going to come up with some nice regularizer that's going to regularize learning so that the solution is going to end up generalizing better. So they're going to write a lot about it, put a lot of theory there, motivation there, inspiration there, and everything. And then what they saw is that, and then eventually they're going to write this down and they say, this is what we're going to minimize. And then boom, results. Somehow that's been minimized. But if you think about it, the actual effort, both time, our mental energy, and actual money going to is the optimization stage. That stage that's been like squashed is where the actual, let's say, beef is, and we want to look into that one. Because it's really like all about optimization. So, and then what we want to know is that if almost every effort is going in the stage of the optimization, what we are getting at is what getting out is probably not just a final model, but there must be a lot of, let's say, different signals that we can use in order to see what happens. And then why does it matter is that as we have already seen earlier from the various places, including, let's say, lottery ticket hypothesis and whatnot, is that these the optimization algorithms that we use are not exploring the full space exhaustively and then find the one amazing solution. It is extremely localized, and then it actually is affected heavily by the shape of the optimization or the loss function landscape. And then furthermore, because the space is so large and all these models are nonlinear with all those, let's say, ambiguities or the symmetry here and there, we get like tons of solutions that are equivalent in terms of the loss function that is computed on the training set and as well as the test set, in fact. This is one of my favorite papers, not my papers, but the papers that I read in 2018. This paper was like, I heard that they rejected repeatedly until it was presented in one of the workshops back then. What this paper did was really simple. It took a very simple, I think the LSTM-based sequence-to-sequence model, or I think this one was a classification, if I remember correctly, and then trained on the synthetic data for the sequence classification. And then what they did was that this data set didn't even have a noise. So train on the training set 50 times, starting from the different initializations. On the test set, every single model gets this problem perfectly, 100% accuracy. But then they also created, because it's synthetic, very simple to create, test set with a slightly more repetition than usual, slightly shorter than usual, slightly longer than usual. And then what you see is that these 50 models that were seemingly identical are very, very different from each other. In fact, actually, these two models are actually amazing. They generalize to much longer sequences very well. And then at the 2020, Garo said, "Oh, this paper. I think this paper was a bit unnecessarily thick. I don't think it had to be that." But this figure is amazing, right? This is one of the easiest figure to kind of use to, let's say, make a point here. Is that the space of all possible decision rules, you can think of this as even a primary space as well, although it's not going to be as well, let's say, behaving like this one. And then, based on our choice of the machine learning model and the data set, so when we say ML model, that is a combination of the data and the training algorithm, we can, explore the space, some subset of the space, and within that subset of the space, large part is where we can actually minimize the training minimize the training loss perfectly. And then with this kind of, let's say, very large non-parametric models that we're working on, most of the time we can find them. But then within that, there's a subset where these models are going to generalize really well. So the test loss is going to be minimized to the 0. But the test loss has to be the set of the examples that were drawn from the identical distribution. It doesn't have to be IID. It could be, but they're at least exchangeable with the joint distribution to be stable. But then within that, in fact, a lot of these solutions are the solutions like these standard ones, that as soon as we change anything slightly, it's going to fail. But then there are subsets of the solutions that corresponds to, let's say, this one. This one is a great solution, right, for the long sequences. But there's no guarantee that this one is this one, could be that one, right? So there are a bunch of them. So eventually what we want is we want to find this tiny solution. And then we know that this happens because a lot of people have been looking into this. And then the McCoy in 2019 already showed that we actually don't even look at the model, right? So if you look at the model, we can always find this kind of examples. That's called the adversarial examples. It says, super high-dimensional space with a finite number of the parameters and still very nonlinear. Of course, there's going to be adversarial examples, but in this case, they didn't even look at the adversarial examples. They look at the problem and they're like, I could solve this problem by looking at the lexical overlap. What if we remove that? And then these models kind of failed. And then they were looking at maybe solve the constituents. Let's create another concept. Models failed it. So we can do it, but this is actually only for the cases where we know where things are going to fail. Again, the reason why I never said it, but the reason why we're using machine learning is to solve a problem that we as humanities have never even imagined that we could solve. Not to solve a problem that we can already solve, but at 1,000 times faster. That's great, productivity boost and everything. But what that means is that there are a lot of problems that we want to solve with the machine learning. Find the new molecules, find the new scientific laws and so on. We cannot do this because those are the things that we don't know what those are. So what that means is that we're kind of, let's say, pretty much doomed because we can't distinguish these solutions ourselves. But then, so then what we need to do is that there are two things we can do. One is we need to think about the assumptions so that we can actually kind of expand it a bit further, or we can try to look for other signals that allow us to, distinguish these solutions beyond just looking at the loss values. And the nice thing is that the optimization is really, really rich phenomenon, in particular for training this kind of, let's say, large-scale non-parametric models. So for instance, this is a paper by my former postdoc, Stan. So we trained the model twice, and then they all got to the same level of the training loss. Essentially, they are same. If you look at just the training loss, they all solve the problem perfectly. But then they are very, very different from each other. So training loss here, these are all literal accuracies. They're literally the same thing. But then the funny thing is that if you look, when we looked at the spectral norm of the, I think it was the covariance of the stochastic gradient, then we can see that they are actually very, very different. And then there's a point at which they diverge from each other, which we, the point which we called it break-even point. Now, there was another paper that talked about the edge of the stability, right? So here's a chaos, so I'll call it exploding gradient, vanishing gradient. We have to always stay in the middle, but then depending on where we fall off, the things change. And then similarly in 2019, another former postdoc of mine, we looked at, okay, so looks like the norm of the gradients, they tend to be really, really similar. They are not that large. I mean, you're not going to find the one stochastic gradient computed on the mini batch that has a norm of the 1,000, another one that has a norm of the 1,000. They are more or less similar. But then if you think about what it means for the stochastic gradient to converge, of course, they never get to zero, right? So it's going to be more like, they are just staying in one of them. So on expectation, they are not moving. What that means is that then, if you ignore the norm, then it's all about the kind of, let's say, distribution, angular distribution. And then when you look at some of these examples, higher the angular distribution, often the better generalization. Although, again, the training loss doesn't really distinguish any of these solutions. And similar thing, learning is not monotonic phenomena. And then the monotonic would be great. Just loss goes down little by little. But as we have seen, for many years now, almost a decade. This is a work from the Chalar Gulsar, who used to be at DeepMind, now at EPFL. He kind of, let's say, made some weird, let's say, the data set, and then was trained on multi-layer perception. And then what happens is that initially the training error just dropped. Exactly the same thing is but then it looks like it's actually getting worse. But then suddenly they drop. Again, training error goes down, but the validation error didn't go down. But then it eventually went down, and something similar. And then this is an interesting thing. This is Phil Blunson, who is now at Coherent Oxford. This is from his talk in 2015 at the CFAR Deep Learning Summer School. Not from many papers. It took me some time to dig that out. But this is on the attention-based question answering model from the DeepMind. And then what happens is that back then it's a validation accuracy. The training loss is just continuing to going down, but then somehow the validation accuracy just stopped for 5 hours, and it just jumps up. Now, these days, what do people call it? Grokking, I guess, right? But we've known that, they all along, yes. I don't think we need another name, but yes, you see that this kind of thing happens. What that means is that there are a lot of, the signals or breadcrumbs along the optimization trajectory. And the idea is that can we then find and use these breadcrumbs, and can we actually identify what those breadcrumbs are? Now, unfortunate thing, and then we need the breadcrumbs because unfortunately we cannot look at the entire trajectory ourselves. That's like 7 billion, or you had a 60 billion parameter model. Yeah, 60 billion dimensional space, and then stochastic gradient is happening, and then if I think that you're using like the 2,000 examples by 2,000 tokens each, so I guess like the 4 million, the tokens at every time. So I don't know, like the month of the trajectory is there. Can't look at it unless we were Jeff Hinton. So what you do is that you just imagine how the optimization happens in 3D space, and then shout out 7 billion, and then maybe Jeff can get the sense out of it. And this is his actual slide from the Coursera lecture from 2012. Unfortunately, not a lot of people are Jeff. For sure, I'm not. So what we decided to do was that when you had my again, former postdoc, and Naomi, who is now at the Camden Institute at Harvard, and Michael and Angie came to me saying that, okay, so we have few other hypothetical, let's say, quantities that we should track and then see what happens with this. I was like, okay, what are those? And then they gave me all those lists. And I was like, but why not this? Why not that? And they're like, oh, they already were explored earlier, not perfectly. And we're like, okay, that's not that great. And we're like, okay, what if we actually let the machine learning figure out what are the important features of the optimized, what are the important breadcrumbs for us automatically. At the end of the day, why are we doing machine learning? In order to analyze or extract the patterns out of the data that we cannot do so ourselves. So let's use the machine learning on top of the artifacts from the machine learning algorithm. And then I brought up the notion of the hidden Markov model. And then you'll be surprised, but I wasn't, because I never teach it anymore myself. No one knows about HMM anymore. People forgot about it. I mean, I think that rightly so. We have so many other things to learn. So we actually went through the hidden Markov model together once more. But the nice thing about the hidden Markov model is that because of the history, there's a really nice, well-done tool. So we can actually use it relatively straightforwardly. So what we did was that we saved all those checkpoints, training multiple times for the models, and then collected all those statistics that we think are suspects as a potential breadcrumbs, except for the loss values, because we think that the loss values are too kind of, let's say, naive, and then it requires us to have a data set. And then just fit it HMM, and then the posterior inference over the state trajectory. And then some of the features we used were the things that people said that they were important for analyzing this kind of optimization, and then some we just added for just random things because we can compute it very easily. Like the median of the bias values, very easy to compute. And then once we fit the HMM, what we get here are two things. First is the transition matrix that tells us what are the latent states, and then how the transition happens from one to another. And then this is a very weak model, of course. It's just a Markov model, right? But still, it tells us about how during the optimization, how the states transition. And then second is the emission distribution. And then this emission distribution tells us about the feature importance for each of the state as well as the transition. So here's an example. We trained the ResNet 18 without batch-norm and without residual connection. I'll tell you why we did it on C400 multiple times. Many times fitted the HMM, once the HMM was fitted, and then we did a cross-validation to find the right number of the hidden state. And then in this particular case, we ended up with 5 hidden states. And then this is a one training run, this is another training run. You see that, okay, these training runs do look very, very different. And then what we see is that in the case of the top one, we started from the state 3. And then it stays here quite a long time, but then it jumps to the state 2, and then to 0, and then to 4. On the other hand, the second one, it got stuck at the state 3 for a long time, and then jumped to 1, and then 1 not. And then what this tells us is that, okay, we prefer a trajectory learning that goes through the state 2. Oh, okay, interesting. So we looked at this grok thing, right? So one of the examples that they were using, or the setup that people have been using, is a one-layer transformer on modular addition. So x plus y, modular 113, pretty arbitrary, but let's stick to that one. And then we train it many times. Now it turned out that the so-called grokking doesn't necessarily happen always, by the way. And then we feed it the HMM, and then we get this kind of state transition matrix or the transition map, or the Michael likes to call it training map. And then everything starts from the state 1. And then often it's going to go to either the state 3 and then 0 and 4, so the first one, or it's going to go to 2, 3, 0, and 4, second one. But sometimes it's going to go into this state 5, and it gets stuck there. Nothing happens. So training loss is 0, but the validation loss is it's actually going up a bit, right? And then we know that the states 2 and 5 are undesirable. But again, we have to look at it manually and decide. Not great. Oh, yes, please.
How are the states defined here?
Sorry?
How are you defining the states?
States just come out of the hidden Markov model.
Right. So do they correspond to specific parts of the trajectory?
Now so the once HMM is fitted, so we use the bound mesh to get the transition matrix as well as emission, the distribution, and then we just run the forward-backward model to algorithm to find the maximum and posterior state. So then you can now map it back. So we thought, okay, that's too tedious. We don't want to look at all those things ourselves. So let's use yet another machine learning algorithm. The simple ones only. We only use a very simple ones, right? ML 101, linear regression. So we're going to make a bag of state visit vector for each of the state. and then just predict the convergence time, how quickly it actually converged. And then it turned out that these coefficients actually tell us exactly the states that we don't want to go there. We call it the tour states. So whenever the training run visited these states a lot, the convergence toward the end took much longer. So we're doing now machine learning on top of machine learning on top of machine learning. This is great. So we're not going to do anything ourselves. So what did we actually learn by doing so? One thing we have actually learned is that a lot of the weird artifacts that we see from training runs are almost always, if not always, just due to the lack of hyperparameter tuning. So I told you that earlier, I showed you this one, and I said that we trained on ResNet 18 without batch-norm and without residual connection. We probably wouldn't call it ResNet, I guess. And then we just put that back in, and then all this tour state disappears. It's just training happens very smoothly for any runs that we try. And then that makes sense. What is the three most important, let's say, the inventions in deep learning over the past 3 decades? One is, one is convolution. One is shortcut connections, like the residual connections. And then 3 is realizing that the SGD works. That's what Leon told us already in 90s, right? So, and then we removed that one. Obviously, it wasn't going to work. We just added back in, done. And it turned out that the same thing with the grokking as well. So we followed the non-dials, the setup, and then their transformers somehow did not have layer normalization. And then also, they were using a very large mini batch. And then if you go to the efficient backdrop by Jan LeCun from 1998, he actually says that what is the best mini batch size? 1, literally. So we're like, okay, let's add back the layer normalization, and then let's use a smaller mini batch. And then these tour state, in particular this 5, just disappeared. And then what we see is that they just smoothly go down. It really tells us a lot about the importance of the hyperparameters, as well as how the hyperparameters affect the whole, let's say, optimization landscape. Yes.
But does actually memory learn per network, right?
Yeah.
And you need to run multiple times in order to learn all the way.
Absolutely.
Does it generalize to like other networks, or
I'll get to that one actually. Oh, that's the future one, right? Yeah, exactly the question I had. Yes. So what it tells us is that this optimization, so all those artifacts we get from the optimization really do have a very, very rich structure as well as information that we can use. Now, we don't know how to use it perfectly yet, but it turned out that we can actually analyze them automatically or systematically using yet another layer of the machine learning algorithms. And that's what we should not be shy about. If you're going to analyze machine learning algorithms that are supposed to help us analyze high-dimensional complex data, we should use machine learning to do so. And then we use a very simple one like hidden Markov model, extremely limited, and then linear regression even more so. We use a backup, state visitation, obviously not a great idea, but this kind of points to the fact that we can actually use the machine learning increasingly more so. So the next steps, so 2 of them, one is that we only did a smoothing. That is that we assume that all the trajectories, so full trajectories are always available. We use them to do the estimation of the parameters, and then we did the map estimation over the states. But what we really want is the filtering if you wanted to use on the fly as the training happens. That's the one thing. But of course, that's not enough. That's not enough because we don't know how to act on it. Think about the difference between how the original common filter was designed and then how we teach the state space model. We often omit the action quite often, but then action had to be there. And that actually means that we need a way to introduce some kind of more of a notion of the causality. That is, if we act on some of the values or the sum of the parameters of the optimizer, how would the next state change? And then on top of that, if we know some of the states are the things that states that we want the optimization to visit, great. If not, we're going to intervene even more. We actually don't know how to do that one, in particular in a tractable way. Now there's a 3. That's more connecting to, can we fit one HMM for all the different models and their runs? In fact, the reason why we use this kind of set of the features that were manually extracted was kind of first step toward that one, because all those networks are all different. But if you look at the overall statistics, they can be somewhat unified. So that's the end of part 2. As I promised, I only have 4 minutes. So the part 3 is probably not going to happen. But is there any questions or the comments on the part 2? Too clear. Oh, that's all right. So I'm going to actually skip this part, except for the pointing out one thing is that this is a figure from the Ferenc, the blog post from 2019, which is actually one of the great, let's say, introductory material to thinking about the relationship between the interventional and conditional distributions, and how that actually, what kind of implications that may have on machine learning. But this is nothing really dramatic, but the data plus graph assumptions is what we always do. And that's the only way in which we can actually go forward in machine learning. Unfortunately, we kind of say, stop talking about it because it's so obvious. What are some of the major assumptions that we almost always have in this in this modern world in many of the majority of the papers is that either the samples are IID or exchangeable. And then we're going to say that the word is static, so everything is stationary, and the test time nothing really changes. And that's it, actually. And that's it. So we don't really specify it, but as we actually solve increasingly more real-world problems, of course, word is not stationary. Of course, we don't want to solve the problem instances that were sampled from the same distribution. I'm going back to the antibody design over and over. By definition, antibody design process is where we need a classifier to classify candidates that do not look at all like the original ones that we had. If we do it, that's just a rediscovery, and then doesn't help us at all. So we started needing to actually talk about the assumptions quite a lot, and then the reason is because our observation is always limited. There are always unobserved variables, and then if we ignore the unobserved variables, we often cannot actually distinguish between the different ways in which the data was generated. And then why does it matter? Is that if we know how the data was generated, then we can actually build an algorithm so that it's going to be robust to the particular types of the changes in distribution over those hidden variables. Now, this is really important part. So we can build an algorithm robust to such a distributional change only if we know what the distribution change is and can be characterized. There's no such thing as a generic, let's say, out of distribution generalization. That's a complete bullshit. I can give you a counterexample. Let's say binary classification, y can be 0 or 1. I'm going to shift the p of y given x to be q of y given x equals 1 minus p of y given x. Obviously, that's going to fail. So the labels are flipped. Unless you specify what the distribution change is, we cannot solve the problem. And then to specify that, we need to rely on this kind of, let's say, how to describe the word in a graphical model or the structural causal model type of thing. But I'll skip this part. And then just to wrap up, so to wrap up, the one thing that we're seeing, and then and at least I'm actually putting some time on, is that it's kind of, let's say, thinking more about what are the assumptions that are important or the necessary, often allow us to revisit some of the very widely used paradigms in machine learning that we've taken as granted. For instance, multitask learning. I don't know why it should work actually still. Does anybody know? Or the multimodal learning, how should it work? I don't know. It's unclear. Continual learning. It turned out that continual learning is not even a thing. Well, we can talk about that. But anyway, so all those things. And then already in 2012, Bernard is another person like Leon who says a lot of, let's say, visionary stuff. And then only after, let's say, 10 to 15 years later, people like me, like the normal kind of machine learning researcher, realized that was correct. He was actually the right thing. So in 2012, Bernard Shorkov and his collaborators had a paper talking about the causal versus anti-causal learning and its implications on the semi-supervised learning. And then there he talks about how the assumption on how the data was generated actually impacts what kind of machine learning paradigm in the particular case semi-supervised learning should or should not learn. And it feels like we can actually push it further. So, and then, of course, distribution shift. So to wrap it up, I'm going to just, invoke Leon to wrap it up for us. So this paradigm has really worked well for us in a very convenient way. That's great. But it's not going to it may not be enough to fulfill our increased ambition. Now, it was 2015, so big data was still a thing. So, but let's just focus on AI part. So of the artificial intelligence. not just building a predictive model on the IID setup, but building an actual intelligence, we probably need to go further. And then there are many different aspects that we all need to collectively explore. I mean, I just pointed out 2 to 3 of them, but I think there is going to be an interesting time. So perhaps the first step we can take is to make sure that we don't hide all those skeletons in the closet, but trying to show it to others. If something doesn't work, gotta tell others. If something was really important, gotta tell others. If something had to be done, gotta tell others, so that we can actually make a collective progress. And Homo is a great, direction. So yes. But anyway, that's it. Finally, thank you.